lecture, we will introduce interfacing with push buttons and LEDs. Push buttons are fairly ubiquitous devices found on many modern-day electronic systems, ranging from watches to scroll through menus and get different information, to video game controllers where you can control the direction of a character or various special action items using the various push buttons on board. Computer mice typically have a left and a right click. You may even have a scroll button on there. Calculators have a keypad allowing us to enter numbers, clear out the calculator, and do any other sort of special functions such as trigonometric functions, logarithms, those types of things. And we see them on almost any kind of a device that requires a user to push a button. So in this lecture, we're going to understand how those buttons are configured and how they can be connected to a microcontroller to determine whether the button is pressed or released. The first thing to understand is that not all buttons are manufactured the same way. So push buttons can be either normally open or normally closed. As you see in the bottom left, a normally open switch has a connector plate that usually rises above two contacts, and then when you press the button, it closes those contacts with a closed path for current to flow. A normally closed switch is the exact opposite, and so if it's not pressed, the contacts are connected via the portion of the button, and then when the switch is pressed, it creates an open circuit. So one of the first things to understand if you're choosing a push button is whether or not you are choosing one that is normally open or normally closed, as that will determine how you interface with it a little bit differently. So let's go ahead and look at a schematic of how these push button switches can be connected. The first thing that we want to note is that when you are working with these circuits, you will want to establish a 5 volt and a 0 volt reference. This will be to distinguish whether something is outputting a logic high or a logic low. So logic 1 will typically be 5 volt. In the case of some microcontrollers, you may have a lower power microcontroller operating at 3.3 volts or some other voltage level, but in these examples we will use 5 volts. So here are a couple different schematics, and they involve pull up or pull down resistors. So depending upon how you want to read from that switch, you will need to connect one of these two ways. So if you have a pull up resistor, as seen on the left hand side here, this rectangle is indicating a resistance, might be 1K or 10K resistor, something like that. VCC is our positive voltage, and then of course ground at the bottom. This is going to be a normally open switch. So if you had a normally closed switch, you may connect this the opposite way and may in fact put the resistors in a different orientation. But for these examples, we will be discussing how to implement this with a normally open switch. So in the case of using a pull-up resistor, as you see on the left side, let's think about what is happening here. If this button is not pressed, you have an open circuit to ground, so there's no connection to ground, and then the connection is from VCC through this pull-up resistor and then into the GPIO. And what will be seen at the GPIO will be approximately the same as VCC. Why is that? Well, when you configure your general purpose input-output pin to be an input, it has a high impedance, and this high impedance will be much larger resistance than the pull-up resistor. And so if you think about this forming a voltage divider between the relatively low resistance of a pull-up resistor and the high resistance of the internal impedance of the general purpose input-output pin, this voltage divider will yield most of VCC coming into the GPIO. Now, what happens if you were to push this switch and connect this circuit? This would close this path, and now you would have a short to ground right here, and so the general purpose input-output pin would see a 0 volt logic low reference. So why is it important to have that resistor there? Well, if you didn't have that resistor there, what would happen when you push that switch? You would have a short from VCC to ground, and that would effectively be 5 volts of potential dropped across a nearly 0 0 ohm resistance path, and that would allow a significant dissipation of current and could cause you to burn up traces on a circuit board or damage your microcontroller. So in this case, this pull-up resistor allows us to determine whether our default logic is going to be logic 0 or logic 1, and it also prevents us from having issues of voltage shorting. In this case, we have a pull-down resistor, and this will behave the opposite way. So when the switch is not closed, now we have a resistance pulling down to ground. There still is going to be no current flowing through into the GPIO pin, and so when this switch is open, we are going to see a logic 0. When this switch is closed, now we have a short to our VCC. So in this case, with a pull down resistor, we are seeing that when the button is pressed, we are seeing an output of logic 1. When the button is released, we are seeing an output of logic 0. When you have this, the opposite is true. When this is pressed, you see an output of logic 0, and when it's released, you see an output of logic 1. So depending upon what you want to happen inside of the microcontroller, if you want there to be a logic 0 when the button is pressed and a logic 1 when the button is released, go with this pull-up configuration on the left. If you want there to be a logic 1 when the button is pressed and a logic 0 when released, go with the pull-down resistor configuration you see on the right. So it's also important to note that just like any other electronic component, push-button switches are not ideal, and there are some issues with interfacing with them. So in the next several slides, we're going to talk about what can go wrong with push-button switches, particularly for critical applications where knowing exactly how many times and when that button is pressed is critically important, and how we can mitigate some of the mechanical issues that exist with this device. So no switch is ideal, and so what that means is you may see what is known as switch bounce or chatter, meaning when you press the button, it may not yield a clean edge of a signal. So you may not yield a clean 0 to 5 volt or 5 volt to 0 depending upon when you're pressing or releasing that signal. For some things that might be perfectly fine. So if you think about a laser pointer, if it tends to oscillate between a logic high and a logic low on the order of milliseconds or microseconds, that's no real problem. And so if you just saw it flicker for a very brief period of time, your eye may not even notice it. Same thing if you had a push button on a flashlight. If it oscillated just a little bit and the LED flickered for just a moment before it settled into either turning things on or off, that is not problematic. But if you're talking about controlling a video game and you've tried to push a button once, but because the circuit connectivity bounced a few times, that may result in deploying a special weapon 3 different times instead of once. It may result in different operation of your character in the game, things like that. And certainly you could think of for more mission critical type applications like military weapon systems. You want to make sure if you push that button once, it in fact is registered as pushing once and is not registered as pushing multiple times. So in certain areas it will be very critical to do a switch debounce, and so we will introduce a schematic here that will help us to mitigate the effects of switch bounce. This illustrates what switch bounce may look like. So if we look on an oscilloscope here, every square in here is 50 microseconds wide. So we see that what is happening here is a switch is changing either from open to closed depending upon whether we have a pull up or pull down resistor, but we're going from a logic 1 to a logic 0. But briefly, when we start that transition, there is this bounce before it finally settles down at the logic low. It doesn't happen for very long. In this case, you can see it's only about 50 microseconds where we are seeing this 1 to 0, 1 to 0, 1 to 0 transition. But if you're trying to count how many times a button was pressed or released, this would end up counting that as 4 rather than just 1 edge transition. And so that's important to note if you're trying to mitigate those effects, that we want to use some other approach rather than just directly connecting that and counting within our software. So we can talk about how to account for that. We can do it either using hardware or software. So let's begin with a hardware-based approach to switch debouncing. This schematic here will allow us to eliminate high frequency noise. That will allow us to ensure that we are only changing from a logic 1 or to a logic 0 output or vice versa if we really intended to do that. And this will use a capacitor and what is known as a Schmitt Trigger in order to mitigate the effects of the bouncing of a switch. So we are once again using a normally open switch. When this switch is pressed, then we will see this connected. When it is released, not pressed, we're seeing an open circuit down here, and that will be important as we are going through. So you should be familiar with resistors and capacitors. In case you're not familiar, let's discuss the Schmitt Trigger, which is over here, and the diode in this circuit. We'll begin with the Schmitt Trigger. The Schmitt Trigger may look like an inverter, but you see the symbol that's on the side. That tells us this is a Schmitt Trigger. The bubble on the front, just like other logic gates, indicates that it is an inverting Schmitt Trigger. And what this means is it's effectively a threshold detection device. It's looking for voltage above a certain threshold, and that will be defined as logic 1, and any voltage below that certain threshold will be defined as a logic 0. And it will output the opposite of that. So if the voltage coming in on the left side of that Schmitt Trigger is low, it will output a logic 1, and if the voltage coming in is high, it will output a logic 0. So it outputs the exact opposite. Effectively, this is built using operational amplifiers that are in saturation. It will use a comparator circuit and either saturate at the positive or negative voltage rail. In this case, the positive voltage rail being plus 5 volts, the negative voltage rail being our ground reference. Diodes can be thought of as one-way streets within a circuit, and so diodes ideally only allow current to travel in one direction. So if they are what is known as forward biased, that means current is traveling into the diode, and if you think about it in terms of the direction where the schematic is drawn, diode current will come in on the base of the triangle and go out the point. That is the forward biased region. In the forward biased region, the ideal diode behaves like a short circuit. And so in this case, depending upon what voltage you have, the current can adjust accordingly, and it acts like there is no internal resistance of the diode. When you have current trying to go the opposite direction, the diode behaves like an open circuit and no current is allowed to flow. So what we're seeing here with this dark black line is the ideal diode curve. In the real world, an actual diode does have a small amount of voltage lost as current increases, and so this is the real diode forward biased region. Also in the real world, if you have a significant amount of voltage going across the diode in the reverse bias region, there eventually is failure of that diode and you end up in the breakdown region where current can go the opposite direction. But you see that this requires a fairly high voltage. And for our application, we will maintain our voltages between 0 and 5 volts, so we will never get into this region. There are some other diodes, specifically known as Zener diodes, and they have a very low breakdown voltage here, and that's very purposeful, but that's outside the scope of this lecture. If you're interested in that, you can learn a little bit more. This dashed line is an approximation of what happens in a real diode. So the ideal diode is this dark line that you see here. The real diode behaves more like this curve, and so we can approximate what's happening in the diode with this dashed line. So let's go back to our circuit and see what's actually happening and how the diode controls some of the behavior in there along with the Schmitt Trigger. So if we go into this circuit and we have our switch open, so if we remember what our circuit looked like here, now we're talking about this switch being open, and so effectively this branch of the circuit is just an open circuit. We're going to leave that off in our first analysis. So we can analyze our circuit this way. What that will mean is that VCC is going to be a higher voltage than what we will see across the capacitor right now. This is open, and this will allow current to flow in this direction. The current flowing this way through the diode means that it is in the forward biased region, and effectively that diode is behaving, if we think about it as an ideal, the diode is behaving like a short circuit. Because it is a short circuit, that means it's effectively nullifying the influence of resistor R2. So that's why you see R2 grayed out there. So the current will flow from VCC through R1, through the diode with effectively no loss if we assume an ideal diode, and then it will start charging this capacitor. As it charges the capacitor higher and higher and higher, eventually the potential across the capacitor will rise to the level where the Schmitt trigger will now say it has detected a voltage above the threshold of influence, and when it sees that, then this will invert and output a logic 0. So after a certain amount of time, once this capacitor has enough time to charge, it will output a logic 0 over here. So what that means is when the switch is not pressed, the switch is remaining open, the capacitor will charge. It will stop charging once the capacitor is charged to the level of VCC. So eventually this will reach steady state. This behaves like a short. There won't be any more current flowing through R1 once the potential here matches the potential of VCC. And so at that point we will be in steady state and we will be outputting a logic 0. Let's go ahead and look at the opposite of when that switch is pressed. That means that we are now closing this pathway here. And so in this case we now have a short to ground, and so now we have a 0 volt potential here, 0 volt potential here. We only have 0 or positive potential across this capacitor. So what that now means is that the potential at this node, VB, is more than the potential at these nodes over here, VA. Because this potential is greater than this potential, that means that now the diode is in the reverse bias region. It has more potential on the point side than it does on the flat side. And so that means that the diode is going to behave like an open circuit, and effectively it is now grayed out because it has no influence when it's behaving like an open circuit. It's effectively just an open pathway. So now what's going to happen is this will behave like a source-free RC circuit, and you will see the current flow out of the capacitor and dissipate through the resistor, and eventually what that will mean is that the capacitor will start to discharge. As the capacitor discharges, it will lower potential below the threshold needed to say there's a logic high on the Schmitt trigger, and eventually what that will mean is that the Schmitt trigger will output a logic 1 because it's inverted. And so if it sees a low voltage level coming through in the left side, then on the outside it will output a logic 1. So now what this means is that when the switch is pressed for a sufficient period of time for that capacitor to discharge, we will start to see a logic 1 come out the right side. So what does this help? Why are we actually doing this? Well, that's because we're relying upon the capacitor to not change instantaneously. So we know that capacitors do not like to instantaneously change voltage. So as soon as you release that switch, as soon as you close that switch, the capacitor is going to either slowly charge or discharge depending upon the positioning of the switch, whether the switch is closed or open. And so because we know that capacitor cannot instantaneously do it, that gives us a certain amount of time for that charging or discharging to happen. And if you saw the quick chatter of what it would look like if that switch was bouncing, that would happen so quickly that the capacitor would not have had enough time to charge or discharge. So we're going to make sure that we set up a significant time constant in here using our resistor and capacitor combination such that we don't charge or discharge significantly in the amount of time that we would expect that bounce to have gone on. And so that is an important aspect of using the capacitor here. So the capacitors, as we know, cannot instantaneously change potential. They can change quickly, but not instantaneously. And then the output from the Schmitt trigger will not change until the capacitor voltage rises above or falls below the threshold of influence. That allows some stabilization in this circuit, even if the signal coming in from the switch is quickly changing. We can also perform debouncing in software. So there are several approaches, and it really depends upon whether it is a critical application, time critical, or whether it is something that we can wait just a little bit on. And so we will look at how to do this. One way is to check to see if we sample various samples of the signal coming off from the switch, and if it stays stable at a logic 1 after a significant number of samples. So rather than just doing a single bit test, we'll do a bit test, do a bit test later, do a bit test later, do a bit test later, and if all of those bit tests come out with the same value, we can be confident that the switch is intending to output a logic 1. If we do a bit test and all of them come out logic low, we can be confident that we have a logic low. Otherwise, if we see some of those bit tests come out as logic 1, some come out as logic 0, and there is no consistency, that tells us that we're potentially in a bounce event and we need to wait and then check again and see if we do have consistent values. So that is one way to approach this. So here is some pseudocode for a time-critical switch debounce. The first thing we're going to do is establish a counter variable. So we'll define our own variable, initializing it to 0 for the count that we've gone through. This will be a count of consistent voltage levels coming out of the switch. We're going to set up a variable to track the switch state, and that will be initially released. So we'll have either released or pressed. And so that will be a binary value that will say it's either released or pressed, and we can use whether we want 1 or 0 to indicate released or pressed. This will just be a binary value, single bit. And then we're going to set up a sampling event. So we're going to sample doing a bit test. We could also set this up in an interval using a timer. We haven't talked about timers quite yet, but we will soon. But we could set up a timer to separate how often we're going to sample. And in this case, we might use a period of maybe 1 millisecond. As you saw in the screen capture from the oscilloscope, that happens very quickly when we're talking about switch bounce. And so if we just sample this at 1 millisecond, maybe even a few microseconds, then we can know when the switch bounce has been mitigated. So every time we do a sample, if the switch signal is high, meaning we're seeing a logic 1 coming off from the switch signal, we're going to reset our counter to 0. And we're going to switch the state to being released. Otherwise, if it is released, then we're going to increment the counter. And we're going to say if the counter has gotten all the way to 10, then we will change the switch state to pressed. So this is just checking to see, okay, is it pressed, is it released? And if we get it consistent in our count for 10 different times, then we can be confident that they intended to press the switch rather than it just being some sort of a switch bounce issue. If something is less time critical, what we can do is just effectively set up a delay. And so if the switch signal is high, we're going to set the switch state to released, otherwise set it to pressed, and call a time delay long enough to bypass the bounce. Just check it once more and then see if it's consistent, and if it is, then we can be confident and set it straightforward. So this just really, instead of doing it 10 times really quickly, we can actually just have a longer delay in there and be consistent. So that's the major difference between what's happening here and what would happen in the more time critical. Before I continue, I would like to acknowledge this website where the schematic that you saw was taken from and several of the examples. So I would like to acknowledge labbookpages.co.uk/electronics/debounce.html. There are some more explanations on this website, and it's very useful if you want to know about switch debounce and how that schematic is working. Before I conclude this lecture, I would also like to discuss interfacing with LEDs. LEDs are a special kind of diode. We've already talked about diodes, but this LED is a light emitting diode. So it's a special kind of diode, behaves the exact same way as a regular diode, with the one added feature that when the LED is in the forward biased region, it does emit light. LEDs come in different colors. There are red ones and green ones and blue ones. Some various other colors as well. And so when you forward bias a diode, it can light up. And that's a very nice thing to interface with some of our GPIO ports so that we can determine the status of something. So you might turn on a light to indicate that we are running in a particular mode of operation. You might have a light that indicates a warning. All those kind of things we use LEDs for. And so oftentimes devices just have a little LED to indicate that there's power received to them or not. And so when we're interfacing with these LEDs, we want to make sure that we configure the port for output. We want to be able to drive the LED. LEDs are not going to give us a signal on their own effort. We want to control them. We want to determine when those LEDs are on or off. And that way you get to decide whether you're outputting a high or low. So making things an output means you, the user, in your software that you define, allow that LED to turn on or off. It is important to note that LEDs are polarized devices. So as we indicated previously, LEDs can operate in the forward or reverse bias region. And if you put in your LED backwards, when you mean for it to turn on, it's going to end up being reverse biased and vice versa. And so you want to make sure that it is connected correctly. And so looking for the cathode and the anode, typically on an LED, if you just buy a pack of them, one leg is longer than the other. And so you want current to go in the long leg and out the short leg. And that is the typical orientation. So the long leg you can think of as being on the flat base of the triangle, and the short leg being on the tip, the point of the triangle, as you think of an LED in a schematic. It's also important to know that LEDs are fairly low current devices, on the order of milliamps. And so you don't want more than about 10 or so milliamps going through an LED. And so typically if we have a 5-volt signal, what we will do is use a current limiting resistor, typically on the order of 330 to 470 ohms, and that will limit our current to somewhere between 10 and 20 milliamps typically. So if you think about 5 volts being dissipated, with it being an ideal diode, we would have all 5 volts across the resistor. In a real world, a diode will dissipate about 0.7 volts. And so in that case, you're thinking about 4.3 volts divided by the resistance that you have there. So that will get you to about 10 milliamps if you use somewhere between 330 to 470 ohms, especially recognizing the tolerance in those resistors. So here are some possible circuits, and it depends, like we had with switches, as to what you want the effect to be. So in this case, you can use your GPIO to output a logic 1 that is an active high signal. And so if you do that on the left side, you output a logic 1 or a 5-volt signal on your GPIO, and that current coming out of your GPIO pin can flow through the current limiting resistor and then through the diode, forward biasing it, and then turn on when there's a logic 1. When there's a logic 0, then you have the same potential on GPIO as you have on ground, and it will effectively be in the reverse bias region with no current flowing. On the right hand side, if you were to connect a 5-volt signal above the current limiting resistor and the diode, then what you want to do to complete the path is to have your GPIO pin output a logic 0 or ground signal. Otherwise, it will be floating and you will have effectively a high impedance, reducing any current flow through the diode. So it depends upon what you want your mode of operation to be. And so you can either have the GPIO pin output a 1, turning on the LED, or have it output a 0 turning on the LED, depending upon whether you have it configured in a schematic that is active high, as you see on the left, or active low, as you see on the right. In several of the upcoming labs in this course, we will use the LEDs that are on board in your trainer kit, and you will see more information as we introduce the lab assignments.